In this video, we will discuss about the synthesis of nanomaterials. As I said earlier, nanomaterials are important class of materials because we can tune their optoelectronic properties with the size. In fact, there are many synthetic techniques that are available to make nanomaterials. These techniques are broadly classified into four main groups. The first, what we have, is the physical methods of synthesis of nanomaterials. Second, chemical methods of making nanomaterials. Then we have biological methods of making nanomaterials. Then finally we have hybrid methods wherein we can combine some of these techniques to make the nanomaterials of particular kind. So in a physical method, further we can classify that into two categories. One is mechanical methods, wherein you try to impart mechanical energy to make these nanomaterials. There can be a couple of them. I have quoted only two here. Like you can have a high energy ball milling. It's a very simple technique which can produce large quantity of materials, and it is industrially viable technique. We'll come back to this later on. And also there is a technique within this that is called melt mixing. You melt other material along with the material which you want to have in a nanoform. Its precursor you mix, and in the process of mixing and heating you try to convert the material into nano size, which is well dispersed in the medium. In physical methods, we also can have other group, that is vapor methods. It is basically nothing but you try to take the material which you would like to have in the form of nanoparticles and try to vaporize it by various processes. Then you try to provide sufficient energy and conditions so that the material's vapor can be converted into nanomaterials. Couple of them are quoted here. One is a physical vapor deposition. Second, laser ablation. Then you can have a sputtering technique, electric arc methods, ion implantation, and many more you can have. Now if you go to second group of synthesis of these materials, that is the chemical methods of making nanoparticles, the simplest and more interesting is colloidal route of synthesis of nanoparticles. Then you have a sol gel method of making nanoparticles. Later I will be discussing in detail about the colloidal synthesis of nanomaterials. In case of biological method of synthesis, you can try to explore biomembranes of various kinds to make nanomaterials. You can also have genetic molecules like DNA and RNA, which can be guiding molecules to make certain nanoparticles. Similarly, one can try to explore enzymes and also microorganisms to make nanoparticles. The last classification, that is the fourth one, is hybrid methods of making nanoparticles. Electrochemical synthesis of nanoparticles, you can try to combine the electric field with the mobility of ions in solution so that you can have reduction, oxidation of these ions. As a result of that, you can make nanoparticles. Chemical vapor deposition is another hybrid technique. Then particle arrest in certain medium, that is also an interesting approach to make nanoparticles. Let us try to discuss some of these, not all of them, but some of them which are important for us as per the syllabus. We will try to discuss them in little detail. So the first one is mechanical ball milling. As I said earlier, the basic concept of this technique goes like this. You just imagine you have an empty drum which is having a shaft on either side, so that which can be connected to motor. I have shown arrow here so that it can be rotated either clockwise or anti-clockwise. That doesn't make any difference. Now you can have the milling balls. What you see small circles, those are nothing but the milling balls, which is supposed to be hard material, which is nothing but a grinder which will be rotated along the wall of drum when drum rotates. So basically we need to load the bulk material, powder, some material which you want to convert to nanoparticles, along with these balls, and put them together and try to rotate it for required time period. The result of that is when the drum rotates, balls will try to move along the wall of container and then they fall down. I have shown one of them here. The result of that, there is impact of this on the material which we want to convert to nanoparticles. Without going into details of this, just I want to tell there are some critical parameters when we make nanoparticles by this ball milling method. The size and the number and the hardness of the balls, what we have here, that is an important parameter. The speed of drum is also an important aspect. The amount of time what you do this rotation, that also decides the final size of nanoparticles. And in fact there are other design aspects come in this technique which will try to decide the quality of final product. Now let us come to the another technique of making nanomaterials. As I said earlier, that is evaporation method. There can be many evaporation methods, but what I have quoted here is the thermal evaporation. So this will be very simple and commonly used technique, because you can simply try to design and assemble this technique. So the basic concept of that goes like this. What you have is electrical lines. A metallic boat is put between these two electric points. Now you try to pass more current, then there is IR loss. The result of that is the board is heated up, and you put the material which you want to vaporize, which you want to convert as a nanomaterials, that is shown here. Now by applying required amount of current, you can try to make the materials to heat, melt and even vaporize. In fact, many materials can be easily vaporized in this way. Then once the temperature becomes higher than the vaporization temperature of material under consideration, the vapors are generated and they move up, they go in almost in these directions. Now you want to convert this to a material, therefore you need to have a substrate that is shown here. Then a substrate on which you want to deposit this material. This can be simply like a glass plate or any other material on which these vapors will go and condense, and of course this substrate is supported by a stand. Here I am showing this is very simple diagram, but the real setup will have still more options. Let us not go into those. In this process you can notice very important thing, like as said, you take a material, you have an electric heater, you heat it to required temperature, you vaporize and vapors will go and condense. But we know that when we heat any material in an open condition and go to high temperature, that is melting or the vaporization temperature of material, then the material will react with atmospheric oxygen. The result of that is material becomes oxide rather than the original material. Therefore, you should have a solid base like this, and then there is a vacuum chamber. What you see here is a chamber. Either it is made up of a metal or it is made up of glass. Since glass is fragile, the modern techniques what we have, they are made up of metallic jars, and to these jars certain windows are kept so that you can observe from outside what is happening inside, whether everything is all right or not. Then before this process is started, it is connected to vacuum, normally a diffusion pump, rotary with a diffusion. It will give you vacuum of 10⁻⁻⁶ stars, and the entire process has to be carried out once the required vacuum is generated. Otherwise the material will react, and what you get is not what you want, but what you get is oxide. Well, there are various critical parameters in such synthesis. I have just quoted heating elements. What you are using as a heating element, that should not be non-reactive, but at the same time it should be highly conducting so that you can use it as a heating element. Vacuum level in the chamber is also an important parameter, because low vacuum there is a possibility of oxidation, high vacuum you can have more pure material. Substrate temperature is also an important aspect, because the vapors come and condense. That temperature of the substrate is important because that decides the final size of materials what you are going to obtain. As I said, the more modern techniques will have modifications. In fact, you can have a cold finger attached from the top that is cooled with liquid nitrogen, so that the temperature of substrate can be lowered to a reasonable extent or to the required level, so that the materials can be converted into a smaller in size. There can be still many more parameters, and it is not important at this stage to discuss them. Couple of techniques which will come under this: physical vapor deposition, laser vaporization or ablation we call. Instead of having a heating element like this, you load a material into a boat like this, but don't heat through electrical current. You can try to pass high energy laser beam on this so that it will try to ablate. Again, there can be evaporation. In laser ablation, evaporation is achieved by putting laser beam rather than heating electrically. Laser pyrolysis is another technique where you take a volatile organic material along with the material which you want to have as a nanomaterials, like metal organic compounds is an example. When you pyrolyze by putting laser beam, organic volatile will go out and the metals will be converted to nanoparticles. Similarly, we can have a spattering deposition. This is a very powerful and interesting technique of doing, which can produce high quality films. Here we are limited with the time and it is out of syllabus. I just mentioned here. Again, there are a couple of techniques available within this, that is DC, RF and magnetron. You can combine DC and apply magnetic field so that the plasma created between two electrodes can be controlled, and result of that is you can produce a better sputtering. Next, what we have is a chemical vapor deposition. Again, it is very interesting technique and a lot of work has been done, but here I will try to give just the basic concept of that. You have a chamber as a long tube. There is an inlet that is connected to volatile organic liquid or a material. Then there is a gas inlet that goes down, and by passing gas you can pass a small amount of liquid through this inlet that enters into this chamber, and here there is a zone where the temperature of this zone can be varied. Typically it goes from 400 to 1200 degrees C. This is a quartz tube, otherwise it cannot be done with a glass tube at higher temperature more than 700 degree. So this region is called a hot zone, and you put a substrate here. Then of course it is outlet. Before you start doing this process, what you need to do is connect it to vacuum, suck out the air that is present. Once that goes out, then you start heating this to the required temperature, and then you connect the gas line. Even in fact you can connect gas line initially itself. The result of that is you have this gas as a carrier which will carry this organic volatile compound, and then it gets disintegrated and the material gets deposited, and depending upon the conditions of all these you can try to have the required nanoparticles. Within this there are a couple of techniques available, like metal organic chemical vapor deposition, MOCVD, atomic layer epitaxy, very thin controlled layers of few atomic thickness can be created. Vapor phase epitaxy is another technique available. Plasma enhanced chemical vapor deposition. This is a chemical vapor deposition, and in addition to temperature you also create a plasma here in the hot zone that further helps to control the growth of particles in a required fashion. The fourth technique what we have is electric arc deposition. It's a very simple. You have two electrodes, and then either by having high current or high field you create a spark between two conducting electrodes, and then there is a soot collected, and the soot what you have, the powder that falls down, can be having nanomaterials of particular kind. But in here the material which you want to convert into nanomaterials must be electrically conducting. Therefore this is very helpful technique, mainly to prepare carbon based nanomaterials. Sometimes you can create the electrodes conducting material along with your material. You can incorporate and make electrodes, then try to do the sparking and finally what you have material will not be a phase pure. It is a material of your choice as well as electrode material will come out as the final product. And since the basic requirement here is conducting electrodes, and that is what is getting converted to nanoparticles, hence the technique is not very versatile. It cannot be applied for many materials. However, the material starting precursors are conducting to which it can be applied. So let us stop this discussion here.